I am Anuradha Mathur. I have been teaching physics at Modern School Vasant Vihar in New Delhi. In our previous episode on solids, we learnt about their internal structure. We learnt the attractive and repulsive nature of intermolecular forces were responsible for the property of elasticity, which is a deforming force is removed from any solid, it regains its original structure. This fact could not go on beyond a particular point. That means, you could not endlessly increase the deforming force and expect the body to come back to its original shape and size. You will also recall that we looked into words like deforming force, which were external forces which were acting on a body. Now, these were such which depended upon the nature of the solid structure, and therefore, you categorize them into three classes. We said if the solid has more length like the rope, then you would be talking about tensile deforming force, and consequently, the restoring force which developed inside it per unit area, you called it stress. The measure of how much of deformation took place along its length was longitudinal strain. Likewise, you also studied about solids for which deformation took place because one particular section of it was displaced, such as in this case of a book, where if you were to deform it by pulling only on its surface, it would deform with a shear force. The base of the book remained where it was, and the displacement on top with respect to the base would be your shear strain, and you could measure shear stress. This was done with solid structures like this mentioned in your books, which had a geometrical shape because it was easy to calculate the area. You also studied about volumetric stress, which would happen if the deforming force was hydraulic in nature. That means, say for example, on a spherical ball like this, if the deforming force was from all directions, that means a hydraulic pressure was acting on it, whereby the ball would shrink in its size, its diameter becoming smaller, but its shape not changing. That would account for volumetric strain, and the internal stress developed per unit area in it would be termed as volumetric stress. Now, we are going to look at the ratio of stress and strain, which according to Hooke's law should be related. We did a graph for that in our previous episode, and we are going to now describe the modulus of elasticity. So, tensile modulus of elasticity is called Young's modulus, and it is measured as the ratio between longitudinal stress and longitudinal strain, and it would be given by F upon A divided by delta L upon L, and it has a unit of Newton per meter square, and its dimensional formula would be m L minus 1 T minus 2, which is same as that for stress. Now, if you look at some of the common materials that are around us and study their Young's modulus, notice that the order of magnitude is 10 raised to power of 9 Newton per meter square, which is a very large value. So, if you look at steel, for example, it is 200 into 10 raised to power of 9 Newton per meter square. In the same table, you can also see the elastic limit value and the tensile strength. Notice for bone you have got two values given, which are given in terms of tension and compression. That means, this is slightly different, and this should be taken into account if you were to measure the elasticity for bone in order to know why a fracture takes place or how you can make a pyramid. So, when you are asked a question which is more elastic, steel or rubber, obviously steel is more elastic as compared to rubber. Why? Because you can break a rubber band by just your hands, but it is not possible to do so for a metal wire. Bone structures, as we were talking about, you must have seen in the case of pyramids, where you have people one on top of the other, and at athletic meets, etc. These kind of structures are often done in school. But you must have seen that only very strong people go below, and the people from junior classes with lighter mass of bone and lighter weight go on top. Engineers and product designers need the value for y. How do we determine the value for y in the lab? It is done by using Searle's apparatus. In Searle's apparatus, you have two wires of about 1.5 meter in length, and let us say you mark one of them as A and the other as B. A is called a reference wire, and attached to it is a weight so that it remains taut all the time, and wire B is the one on which you apply some load, which will cause it a tensile deforming force, that means trying to elongate it. A micrometer is used in order to find how much of elongation is taking place with respect to wire A. And having gotten all this, you can therefore find the diameter of the wire and calculate the restoring force which is set up within the wire B, which would be your stress, and then calculate the value for y. And so, your working formula would be y is equal to mg into L upon A into delta L. Shear modulus, on the other hand, is represented by G, and it is given in terms of shear stress and shear strain. So, how do you measure this thing? This is a very simple example here, in which only one portion of it, that means the top layer, is moved, say boxes, cartons, etc. like that. So, what do we do? You can measure it in terms of, say you have this book and you keep this edge of the ruler alongside its beading, and when you pull only the top cover by using suitable force, you find it is displaced to a certain extent. This displacement can be measured, and you can also find out this surface area by multiplying the edges and finding a product for that. The value of your force is known, so the shear force can be calculated, and therefore, you can also calculate the shear stress and the shear strain. So, you have seen you can find the value for G in the lab for some objects which are not so rigid, and you find that its value is given in terms of Newton per meter square. Its dimensional formula remains m L minus 1 T minus 2. Looking at this chart, you will see that for most of the materials, this value of G is almost 1/3 the value for Young's modulus. That means, if you had a plastic cube which was solid and you were finding out its Young's modulus, then it would have a certain value, and if you did the same for shear modulus, it would be 1/3. So, the same material will have different values for Young's modulus and shear modulus. Let us take up a problem. If you have a square lead slab of size 50 centimeters and thickness 10 centimeters, the lower edge of which is riveted to the floor, a shearing force of 9 into 10 to the power of 4 newtons is applied on the narrow face. How much will be the upper edge displaced? You can visualize it something like what we did with the book, and when you solve it, you are going to find that this displacement is 0.16 millimeters. So, this value is very small and has to be carefully measured. However, when you do this problem, it gives you an idea about how much of shearing force is required if you want anything to deform or if you do not want it to deform. Next, we go on to volumetric stress and strain. The ratio of volumetric stress to volumetric strain is known as bulk modulus. It is represented by B, and it is very special. Notice, if I were to give this ball a hydraulic deforming force from all sides, I am going to diminish its size. That means, I am going to make its volume less. So, positive pressure on it is going to make its volume become less. Therefore, the value for B is associated with a negative sign. It is given as B is equal to minus P upon delta V upon V. The rest of it does not change very much, and this value is given in terms of Newton per meter square, and it also has the same dimensional formula. Bulk modulus of some of the materials are given: aluminum, brass, copper, same as those were in the earlier list, including steel. But there is no such straight relationship between bulk modulus and Young's modulus as we had seen in the case of shear. Compressibility is another very important value, and that is 1 upon B. It is the fractional change in volume per unit change in pressure. These are some of the moduli that we consider for solids. In real life, how is it important to us? Let us consider the chairs that we sit on, the shoes that we walk on, the flyovers or the bridges that we step on. All these things are engineering marvels, you can say. You can change the value of Young's modulus by changing the value of the material that it contains. For example, tires etc. that are used for vehicle are all made of rubber. They are the same as the eraser that you use in your geometry box, but they have a content of carbon which is designed to take on the weight on the road of the vehicle and designed to take the elasticity with the bumps on the road, etc. One of the other things that you need to see is that how does this elasticity change the way we design things. For example, the ropes that are used for cranes, they are not solid, they are made up of thin wires. Why that is required? Let us see from an example. For example, if you had to lift say 1 ton of material or a box which is about 1000 kg, then your requirement for steel rod would be about 6 centimeters diameter, which is reasonably high, and therefore, this would be solid and not flexible at all. So, what is done is that you have this thin wires like this which make up the entire rope in this manner. That means, you do not compromise on the strength of the rope and you change it by making it as a composite unit of thin wires, so that it has its flexibility and it can be used wherever you require it. Beams are used in bridges, in flyovers, railway tracks. Why is that? Because you do not want the load that comes on it occasionally, that means with traffic, when the load comes on it, it should not buckle under that. Therefore, I-shaped beams are used. That is a special design which is ready to take on the deforming force and develop the requisite value for stress within it, so that for small strains it is able to maintain its elastic property. You do not want any of the bridges collapsing. One other example which strikes us, ordinarily we do not think about it, are the sand piles or the gravel piles at construction sites. When it is loaded off from a truck, it piles up in a particular conical shape. Why is that happening? This is because of shear property. How does shear come into the picture? We are going to just look at it from this example. Why is the height of a mountain a certain value? Why aren't all mountains higher than Mount Everest? Why is Mount Everest so unique? What happens is that the weight of the mountain falls directly on its base. The sides of the mountain are free, and because of this it is not a case of compression. So, what happens is when the weight falls on the base, the sideways force starts off as stress. So, the stress between the rocks or the rock material at the base is responsible for how much of force it can withstand from above. That means, the deforming force that accounts for its height. Now, let us calculate the highest height that you can have for a mountain on earth. This maximum height calculation is not that difficult. We are going to do it in a very simplistic way. Let us say that the elastic limit for a typical rock is 30 into 10 to the power of 7 Newton per meter square. So, to calculate the weight of the mountain, we will need its assumed height and the density and g. So, we will assume that the density of the material of the mountain remains the same, which let us take it as 3 into 10 to the power of 3 kg per meter cube, and let us assume that the value for acceleration due to gravity also remains the same and does not vary with the height, which it does. So, with all this assumption, we can calculate the value of h, and that will be 30 into 10 to the power of 7 Newton per meter square divided by 3 into 10 to the power of 3 into 10, and that will give us approximately 10 kilometers, which is more than the height of Mount Everest. That means, you cannot have a mountain on earth, if these were the specifications, higher than Mount Everest. Why is Mount Everest only the highest one? Why aren't there mountains like this all over the world? They could have been, there are mountain ranges, but perhaps the shear force does not allow this height to be placed on any other portion of the earth, and that is why Mount Everest is the highest. So, today you have seen in this episode with solids the 3 moduli of elasticity, which were for 3 special shapes, one more in length, which were like rods and wires or thin strips of metal. The others were solid structures like for boxes or say solid square pieces or rectangular cuboids like that, or shaped like a sphere like the ball that we had considered. So, therefore, you can find the value of elastic moduli, have a comparison for a particular object. You can also find this by doing suitable experiments, and then we went on to see some applications in real life using the modulus of elasticity or our small knowledge about elasticity. After all, there is a lot to learn about mechanical properties of solid vis-a-vis elastics and plastics.